Dipole-dipole interactions are telling us almost everything we need to know just in their name. It's telling us that we're going to have a dipole. Notice the hyphen is separating the idea from the next idea. The dipole is interacting with another dipole. And in the process, we're going to have a partial positive and a partial negative charge that are interacting with each other. So remember that on these polar arrows, the plus arrow head and the negative arrow head are drawn like so. You end up having your partial negative and partial positive. We replicate the same thing on its neighboring molecule. We've got a partial negative and a partial positive, and these two are going to attract each other across the gap between the two molecules. That stickiness is going to be worth 5 to 25 kilojoules per mole worth of stability, and that's a pretty good amount of bonding. Not quite as much as a covalent bond, but a significant portion. This is going to be something that happens a lot when you've got a really polar covalent bond on this side and another very polar covalent bond on the other side. In that case, you're going to be able to have a dipole-dipole interaction. Now suppose that we've got an even more extreme case. Suppose that one of these molecules happens to be, one of these atoms happens to be very small. So there's a minimal amount of shielding. Remember the amount of electrons that are inner shell blocking the outer shell electrons' view of the nucleus. Well, if we don't have a whole lot of shielding, we're going to have an even bigger effective nuclear charge. We usually do that calculation in a simple subtraction way, but if we're doing it in a high-end supercomputing cluster way, we'd actually get decimals and things. And it tells us that for a very small atom, we get a really big effective nuclear charge. And we don't have things that are much smaller and still electronegative. Best cases of those are going to be fluorine, oxygen, and nitrogen, right? Up there in the upper right-hand corner of your periodic table. That's where it's going to be very large. Now, if we happen to have some of those molecules involved, and they're paired up with a hydrogen atom, those hydrogen atoms are also going to be middle of the road for electronegativity. They're going to be good at sharing, but also at giving up while sharing. And they're going to be easy at taking a positive partial charge, which means that they're kind of the perfect storm for having a dipole-dipole interaction. So much so, and so strong, that we give them a special name. Those are called hydrogen bonds. So in a hydrogen bond, we're going to have a really high partial charge on one atom, a high partial charge on the hydrogen atom attached to it, because that one's a big charge as well. And sitting across the gap, we're going to have some other atom that's got a big electronegativity and a lone pair of electrons sticking out. Now, that's typically going to be nitrogen, oxygen, or fluorine. These are what I'm calling the magic 3 atoms when it comes to hydrogen bonding. Very electronegative. They're bonded to hydrogen. It's going to take the electron most of the time and have a very polar bond in a very tiny volume of space. As a result, you're going to have a really big amount of polarity there. And if we have something like water, what you're going to have is such a strong partial positive here and a strong partial negative with electron pairs on the other side that it can bond very tightly. Now this is an example where we have the same molecule on each side of the gap. What about an example where we have different molecules on each side of the gap? Well, you've seen that almost certainly when we've talked about DNA and other coursework. In DNA, you're going to have thymine and adenine. They make 2 of these hydrogen bonds between them, because on this one you're going to have oxygen. Notice that it's one of the magic 3. On the other side, a hydrogen that's bonded directly to nitrogen, also one of our magic 3. The nitrogen-hydrogen bond is going to be incredibly polar because of all those features that we just brought up. That makes hydrogen have a really big partial positive charge. Oxygen's got its big partial negative and a pair of electrons sticking out toward the hydrogen. It's going to latch onto those very strongly. And the same idea happens down here where we do have the same atom on each side. We need to have it set up so that we have one of the magic 3 on each side, but they do not necessarily have to be the same thing. And that's what you see down here. They're saying A bonded to H, a gap, and then B. A and B can be the same one of these 3 atoms, or they can be different atoms. As long as they're both from this subset, and this is critical, as long as the hydrogen is bonded directly to it. If you have something where there's like an oxygen bonded to a carbon, and then you've got the hydrogen, make that a double bond, that would not be capable of doing a hydrogen bond by itself. Now, if you had something on the other side where it was a water molecule, perhaps, magic 3, hydrogen, magic 3. This would be, actually I should have a big yes there for hydrogen bonding. I don't want to draw as a plus. We'll say yes, hydrogen bonding is possible. If we had 2 of this molecule over here, and remember this is just more stuff sticking off to the side, we have another double bonded oxygen, and we're going to have a hydrogen. Yes, this is going to be pretty polar, but you don't have one of your magic 3 over here helping to tug around the electrons. You don't have one of the magic 3 over here to tug around on the electrons either. As a result, this isn't going to be able to pull away the hydrogen's electrons well enough to make it the big partial positive to stick. What I brought up over here isn't the critical issue. That's just kind of a side note. The key part is not oxygen or hydrogen or oxygen, fluorine, or nitrogen attached to hydrogen. So that one can't do hydrogen bonding as a result. Now, you can also see a lot of that phrase right here. Hydrogen's going to have a partial positive, and it's attracted to the electron pairs on these. Hydrogen's also usually bound to one of those atoms. So we're going to have an A-B kind of arrangement. I also want to point out bigger atoms, on top of having the shielding, they're not going to let the hydrogen get close enough to really start grabbing some of those electrons. And so all these features together are going to lead to it not being as strong if it's not one of these magic 3. So hydrogen bonds end up being very strong. Notice that instead of being in the 5 to 15-ish range, I guess it was 5 to 25-ish, we're saying it's more like 10 to 40 kilocalories per mole for each and every one of these hydrogen bonds. Notice that that means you could get as much as maybe 80 kilojoules per mole of stability from those 2 hydrogen bonds in DNA for one set of base pairs. That means you've almost got a covalent bond of strength between them. That's why DNA sticks together so well. And for the other 2, C to G, that one actually gives you 3 hydrogen bonds. So you're going to be somewhere in the probably 90 to 120 kilojoules per mole attraction range, which is getting into the range of covalent bonds again. So that's going to make really, really strong connections between DNA base pairs. And don't forget, with DNA, you've got so many of these base pairs in a row, it acts like a big zipper and really holds the thing together.